Hi everyone. Today we are going to study under gravitational field application of gravitational field. First one we are going to study about geostationary satellites. Geostationary satellites. We need geostationary satellites to exchange data for communication processes and to send data from one point to another point. That kind of satellites should be stationary relative to the Earth. If any satellite is stationary relative to the Earth, it is known as a geostationary satellite. Then normally they should be launched 36,000 kilometers above the surface of the Earth, and from the center 4.24 10 to the power 7 meters. Actually, we can calculate them. First, we are going to study what is the exact meaning of this geostationary satellites. Actually, to study this, you need previous theory parts also. Gravitational force equation, you need G capital M simple M over R squared. We know gravitational force between any 2 point masses. We can write by this equation G capital M simple M over R squared. This is capital M, this is simple M. Attraction between them. G is 6.674 10 to the power minus 11. Capital M, this mass. Simple M, this mass. F means attraction, you know, they are action and reaction pairs. R, distance between center of gravities. Center to center. We need this equation first, and we need potential equation also to find the total energy of a satellite. Potential, we know potential means energy need to bring 1 kilogram from infinity to point considered. That equation we learned, it's G capital M over R. Here you know force, its units. Gravitational potential means energy need to bring unit mass from infinity to point considered. It's a negative value. Units, joules per kilogram. And you should know potential energy of two particles. Then here energy stored in one mass, unit mass. Then energy stored in mass m, we can find with this equation G m over R. Potential energy minus G capital M simple M over R. Joules, energy of capital M, simple M, both. Actually, this equation gives energy of both objects, not energy of one of them. It was invented by Kepler. This gives total energy of both particles. You should know that also. And gravitational field intensity, I told you, at a distance of r from a mass m, gravitational field intensity is defined as force acting on unit mass. Force acting on unit mass, it is actually F, you know, G m over R squared. Then force acting on unit mass, this should be divided by simple M. Then you have corresponding field intensity here, G dash. It is actually a positional gravitational acceleration, because you know force over mass means, according to Newton's law, F equals ma, acceleration. That means free fall acceleration at the corresponding point. And it is equal to field intensity, also force acting unit mass, and positional gravitational acceleration. That equation you can take from this G capital M over R squared. This is force acting on unit mass, units newtons per kilogram, and Newtons per kilogram means you can simplify that. Newtons means kg ms minus 2. Then kg will be getting cancelled. This also equal to positional gravitational acceleration meters per square second. That means if you place 1 kilogram here, force acting on that this much, and if you drop some object from here, its acceleration towards the big mass also this value. That's why it is known as positional gravitational acceleration also, right? Gravitational field intensity and positional gravitational acceleration. Basically, we need these equations to find energy of a satellite, velocity of a satellite, altitude of that, and total energy, binding energy, everything we can find using these equations. Now, first we are going to study what is the exact meaning of a geostationary satellite. Assume this is the Earth. It doesn't need to be Earth always. It can be another planet also. I told you any object orbits about another one, then that is known as a satellite. Electron is a satellite. Earth is a satellite because it moves around the sun. And moon we can consider as a satellite because it rotates around the Earth. And actually, satellites are there for communication, data, for military processes, and for weather requirements, right? Then what is geostationary satellite? Earth rotates this direction. Then if we can orbit a satellite, so the satellite will be stationed related to the Earth. That means corresponding to the Earth, initially assume satellite is here. When Earth rotates, satellite should move together. Then always compared to any point of the Earth that is stationary. When you look up, it will be there at the same point. After a few hours, you can see at the same point. That means relative to the Earth, that should be stationary. To happen that, this satellite should have same time period of the Earth. Same time period of the Earth. I can draw its orbit like this. Right? It should go through the equator plane. We can study the reason. Assume there is an observer. Satellite is vertically above the observer. Then this man can see this satellite vertically above. Earth rotates. Earth rotates. When Earth rotates, man moves with the Earth, no? When man comes to here, again satellite should be vertically above the man. Satellite should be here. Earth rotates. When man comes to here, satellite should be vertically above the man. When man comes to here, satellite should be vertically above the man. That means that satellite should have same angular speed of the Earth. Then time period of the Earth we know 24 hours. Then this satellite should move around the Earth in 24 hours because they should move together. Then always first requirement, satellite should have same time period of the Earth. 3 requirements are there. First one, time period of the Earth should be equal to time period of the satellite. Second requirement, when Earth rotates this way, satellite should move in the same direction. In the rotating direction, satellite also move. Otherwise, what will happen? When Earth rotates this way, if satellite goes other way, then it will not be stationary relative to the Earth. It should be stationary relative to the Earth. Then both should rotate in the same direction. Then motion of the Earth and motion of the satellite should be in the same direction. That is the second requirement. First one, time period should be equal to 24 hours, time period of the Earth. Second one, it should rotate in the same direction of the Earth. There's another requirement also very important. This satellite should go through the equator plane. That means orbital of this geostationary satellite, this orbital plane should go through the equator plane. Equator plane. Otherwise, we can see a big problem is there. Otherwise, assume if you want to orbit another satellite, geostation satellite, a little above the equator or little below the equator, what will happen? Let's check. Now, these two are not possible. Why? You know, gravitational attraction always acting towards the center of the Earth. But to keep it along the circular path, you know, it needs centripetal force. It is, you know, mv squared over r. Therefore, this force we have to resolve. This force will resolve towards the center of the circle. If you resolve this force towards the center of the circular motion, then other component, normally we have to resolve vector in two directions. First one, if you resolve first one towards the center of the circle, another one you have to rotate, you have to resolve perpendicular to that. Then you can see this force helps to travel along circular path, but there's another force. Therefore, it should go down. It should go down. As a result of this force, it will travel along this kind of sinusoidal path. Therefore, definitely, this should travel along the equator plane. If it doesn't go along the equator plane, it will oscillate between two circular paths. Then it will not be stationed related to the Earth, because when Earth is here, at a certain time it is here, right? When Earth is rotating this, it goes this way, but going down. Then relative to the Earth, it moves down. It's not a geostation satellite. Then what are the conditions? First one, time period should be equal to time period of the Earth. Second requirement, it should rotate in the same direction of the Earth. Third requirement, that orbital of the geostationary satellite should coincide with equator plane. Right? These are the requirements. And how do you find radius of this geostationary satellite? Radius of this geostationary satellite, we want to find that. Assume velocity v and assume time period t. Then we can apply basic equations. You know, for circular motions, we can apply F equals mv squared over r, or we can apply F equals m r omega squared. Then I'm going to apply F equals ma for this satellite to find the radius of the orbital. F equals g capital M, you know, mass of this Earth, mass of the satellite, simple m, gmm over r squared. R means distance between center of gravities. Distance between center of gravities, capital R here. Center to center, gmm over r squared. This should be equal to, we have two equations, mv squared over r and mr omega squared. Circular motion equations, you know, F equals m v squared over r, and we have another equation, F equals m r omega squared. I'm going to take here this equation because we need a time period now. Omega we know 2 phi over time period, therefore I'm going to use this equation. Then for this circular motion, this is the force. That force should be equal to what? mr omega squared. m r. What is r? Radius of the circular path. Radius of the circular path, capital R. Omega squared. Then this is a basic equation. Then actually G capital M. G capital M we can remove by using a mass located on the Earth's surface. Consider any object placed on the Earth's surface. We know attraction, mg, and radius of the Earth, simple r. Then I can apply Newton's gravitational law. You know, this is Newton's gravitational law. G is universal gravitational constant. It's 6.674 10 to the power minus 11. Then here we know mg is the force when object is placed on the Earth's surface. It is also equal to force given by this Newton's gravitational force equation. G capital M simple m over, what is that? Separation squared. Now separation simple r, radius of the Earth, r squared. You know, simple m can be cut. And we have G capital M equals gr squared. Then instead of G capital M, you can use gr squared, because gr squared well known values. G we know, acceleration on the Earth's surface approximately 10, and radius of the Earth we know 6.4, 10 to the power 6 meters. Then instead of G capital M there, we can write gr squared. G simple r squared. Simple m is getting cancelled over capital R squared equals r omega squared. R omega I can write 2 phi over time period. 2 phi over time period. You know, this time period should be how much? Time period of the Earth, and omega squared should be here. Now you can calculate radius of this orbital, geostationary orbital. R cube here equals gr squared. Then t squared is going up, 4 phi squared is going down, t squared here, 4 phi squared here. And you know, here another thing we can prove, it's also Kepler's law. You can memorize that for MCQs, right? Time period is squared proportionate to cube of the radius, because this part is a constant of Earth's radius, gravitational acceleration on the Earth's surface, phi we know 22 upon 7, therefore t squared proportionate r cube. Now you can find radius of the orbital of the geostationary satellite, G r squared t squared over 4 phi squared, and to find r we have to take cubic root equals r. Then what are going to substitute here? G, you know, we derived this using this particle. Then it is located on the Earth's surface, then acceleration on the Earth's surface 10. Then you can substitute 10. Phi 22 upon 7, normally phi squared 9.86. Phi squared normally 9.86. Therefore, you can remove phi squared with 9.86. G normally you can take 10. Radius of the Earth 6.4, 10 to the power 6 squared. Time period, you know, time period of the Earth. Time period of the Earth, we know 24 hours. 24 hours you have to convert into seconds. 24 into 3600 squared. Then calculate this radius, you will get, it is up to you actually, you can substitute values and use log tables to find the answer. Then you can take final answer 4.24 10 to the power 7 meters. From the Earth's surface, it's 36,000 kilometers above. 3.6 10 to the power 7, you can check that, because radius of the Earth 6.4 10 to the power 6, you can subtract this from that value from this to find the height to the geospatial satellite, right? You know, this r means radius of the Earth plus height. You know, this capital R means center to center. It is equal to radius of the Earth plus height to the satellite. Then you can find h also. H is equal to this minus radius of the Earth 6.4 10 to the power 6. Then I think you can do that alone and find total energy also. How do you find total energy? Then to find total energy, you need velocity of the satellite. Velocity of the satellite. How do you find velocity of the satellite? F equals same thing, G capital M, simple M over R squared is equal to, I am going to use now mv squared over R to find the velocity. M v squared over radius of the circular path capital R, then capital R is getting cancelled, you can, M is getting cancelled, you can find velocity square root G capital M over R. This is the velocity of the corresponding satellite. R we know 4.24 10 to the power 7, you can calculate that. I am not going to calculate it now because it takes a little bit significant time. Then R you know 6.4 10 to the power 6, G is 10, time period 24 hours, phi we know 22 upon 7 and phi squared approximately 10. Simplify this and it's up to you. Then after finding velocity, you can find total energy of the satellite. How do you find total energy of the satellite? You know, this satellite has kinetic energy and potential energy both. Then total energy is equal to kinetic energy and potential also, potential energy. Kinetic energy we know half mv squared, right? Half mv squared kinetic energy, half mass into velocity squared. Velocity we know, this squared gm over r only, then half m v squared gm over r. Potential energy we know negative value. I told you we can't make it positive. If you want to make it positive, you have to go to infinity, right? Therefore, potential energy is a negative value. It's G capital M simple M over R. Then simplify this, you can find total energy here 1 GMM over R, here half GMM over R, then difference of them you can see here 1, here half, difference minus half, because half minus 1 minus half. Therefore, total energy minus half GMM over R. To find velocity, radius, actually no need mass of the satellite. But to find total energy, you need mass of the satellite also. Then half difference of them, G capital M simple M over R. This value is not a constant value, it depends on mass of the satellite. Some satellites mass range 1000 kilograms to 1500 kilograms. Small satellites also there. Normally 1000 to 1500. One of the satellites is there which is rotating around the Earth, North Pole to South Pole. We are going to study that later. Its mass is 1226 kilograms. Then normally mass range 1000 to 1500. Whatever the mass you have to substitute here. If you want to remove again G capital M, no problem. Use this one again. G capital GR squared. Then you can find total energy of the satellite. I told you if any object orbits another one, its total energy should be negative. We can't make it positive. Energy of an electron negative. Energy of the moon negative. Energy of the earth negative, because they are rotating around another one. If any object rotates about another one, always total energy negative. We can't make it positive. If you want to make it positive, only one method is there. You have to move it to the infinity. I told you that energy is normally known as binding energy. We did that. No need to do it again here. Then this is gravitational total energy. And here normally astronauts in a satellite experience weightlessness. Astronauts in a satellite feel weightlessness. What is the reason for that? They feel weightlessness, but actually you can see gravitational force is there. There's a reason for that, right? Astronauts in the satellite experience weightlessness. That means these satellites act as free-falling objects because it bends towards the Earth always. It bends towards the Earth always. That acceleration, bending acceleration, centripetal acceleration is equal to positional gravitational acceleration. We can see that, very simple thing. Let's do. We can find, this is true for any satellite. We can find centripetal acceleration of a satellite. Centripetal acceleration, that means acceleration towards the center of the Earth. You know, V squared over R. MA, this is acceleration. V squared over R. Centripetal acceleration. V squared over R. Then we can substitute values here. Velocity we found, velocity was G capital M over R. Then we can find that velocity squared. Velocity squared, you can see G capital M over R. G capital M over R into, that is V squared, this R. What is this R? Radius of the circular path. Radius of the circular path, capital R. Then this R, 1 over R. Therefore, you can see centripetal acceleration G capital M over R squared. And what is the gravitational acceleration, positional acceleration at this orbital? We have equation for that. What is that? Field intensity equation, G dash. G dash is equal to Gm over r squared. Positional gravitational acceleration, you can see Gm over, this was proved. I proved this one, but this one by definition we are taking. Force acting on unit mass, G capital M over r squared. R means corresponding altitude, capital R. You can see both are same. What is that? Centripetal acceleration of the satellite. It bends towards the earth always. That centripetal acceleration is equal to gravitational acceleration at that point. That means that satellite acts as free falling object. Free falling object. It bends towards the earth with the corresponding gravitational acceleration. Therefore, it acts as free falling object. Astronauts feel weightlessness. We can prove that. Consider satellite here. There is an astronaut here. Assume mass of the astronaut m. Weight towards the center. Weight towards the center of the circle. I am going to apply F equals ma. Weight mg. Gravitational force simple mg. Simple mg. What is mg? Mass of the astronaut. Take it as m naught. Mass of the astronaut. G. mg is the force. What is g? Positional gravitational acceleration. This value. Gm over r squared. And when this astronaut is on the platform, reaction given by the platform, I can draw it here clearly. Astronaut is here. Weight of the astronaut towards the center mg dash. Mg dash, you know mg dash means gravitational pull, mg dash, and reaction given by the platform. Reaction given by the platform on the astronaut, capital R. Then resultant force towards the center of the earth, this minus r dash. mg minus r dash reaction should be equal to ma. ma. We know ma. What is a? V squared over r. V squared over r. Then V squared we know Gm over r. Gm over r. Ma, what is A? A we know V squared over r. V squared over r. R radius of the corresponding orbital. Then you can see mass of the astronaut and acceleration m v squared over r. Then you can see these two are getting cancelled. Then you can see r dash becomes 0. R dash becomes 0 means force acting on the legs on the astronaut, r dash 0. There is no reaction between the satellite and that astronaut. Then they feel weightlessness. Weightlessness. And you should know this also. I told you this satellite acts as a free falling object. If it acts as a free falling object, there is no upthrust when liquid is placed there inside the satellite. When water is heated, you can see this in past papers, I think 2005 or something. When water is heated, natural convection currents will not form. To form convection currents, upthrust should be there. Upthrust is given by V rho G, but here it acts as free falling object. Therefore, if water or any object falls under gravity, upthrust becomes 0. Therefore, no upthrust, no convection currents. Then astronauts feel weightlessness, and inside of this kind of satellite, no convection currents because they feel weightlessness. Main reason, it bends towards the earth with gravitational acceleration, positional gravitational acceleration, as he proved. Right. This is the first satellite that you should know, geostationary satellite. Actually, we have in practically three varieties. First one, geostationary satellite. Second one, polar satellites. Third one, Lagrange satellites. Then polar satellites and Lagrange satellites are not there in the syllabus directly, but you can see 2011 there's a paragraph question. Everything was explained. It's about Lagrange satellites. And polar satellites also very important. Actually, you can understand that. Therefore, I'm going to explain about them a little bit. I think they will be very important for next AL papers. Then we have three varieties. First one, geostation satellites. That weightlessness is not only for this. For any satellite, this happens. For any satellite, only any Skylab, right? This happens. They feel weightlessness, no convection currents. Then basically, you know now, geostation satellites. Next one, we are going to study polar satellites. Directly, it is not in the syllabus. But actually, with your knowledge, you can understand that. And Lagrange satellite also not there in the syllabus, but there's a paragraph question 2011 about that. It's very, very interesting principle. We can study about them. First, I'm going to explain about polar satellites. Polar satellites. They are traveling from North Pole to South Pole, not in the direction of the rotating, right? We know Earth is rotating this way now, not that direction. Polar satellites are going from North Pole to South Pole in this way. We can use them for weather purposes, to take photographs, for agriculture and military purposes, right? Entire Earth can be covered by one satellite. Actually, according to Arthur C. Clarke, actually using 3 satellites, we can cover entire Earth together. But normally we have one satellite, many satellites along that orbital. They are traveling 14 times per day. 14 times per day they rotate, and they can cover entire Earth twice a day. Then we can calculate that very simple, because if it rotates 14 times per day, you can find time period of that. 14 time periods means 24 hours. Then you can find time period of that polar satellite. After finding time period, you can find radius as you did before. Then they are traveling from here to here along this kind of orbital. Actually, assume North Pole here. At the beginning, satellite is here. That is the first position. Assume it can cover Earth. Certain angle it can cover. That means it can take photographs of a certain area. Assume here to here it can take photographs. A to B. This satellite can cover from A to B. You know, when this satellite is going this way, Earth is rotating. When satellite is going this way, Earth is rotating. Therefore, this band can be covered, but when satellite goes this way, this point A goes this direction because it is rotating. It is rotating from A to B. When point A comes to B, that satellite should complete one rotation. When this point comes from A, this point A comes to B, B goes to somewhere here, new position of B, new position of A dash, new position of A dash. Then when that point travels from here to here, satellite should come to here again. Initially satellite here, it completes this rotation. When it completes one rotation, that A to B part should go from here to here. Then it can cover entire Earth. Then it can take photographs like this. A to B. After that, at B, A will be here. A dash to B dash. Next time you can see this rotates more. When it rotates again, when A dash comes to, when this point comes to here again, satellite should come to the same point. Then it can cover entire Earth. This kind of passages it can cover. This kind of areas it can cover. Then by 7 rotations, it can cover entire Earth. Entire Earth. Then 14 times it rotates in a day. Then it can cover Earth 2 times. Then using that, try to find radius of this orbital. How do you find that? Time taken for 7 rotations, 14 rotations, 24 hours. 24 hours. Then for one rotation, 24 hours into 3600 divided by 14. Time taken for one rotation. That is a time period. If you know the time period, you can find radius of the orbital using the previous equation. F equals G capital M simple M over R squared. You know R means separation here to here. And you can write mr omega squared, mass of the satellite, R omega squared, omega you know 2 phi over time period. What should be the time period here? It orbits 14 times around the Earth per day. Then 24 hours divided by 14, that time period here. Square of whole thing. Now you can find radius of this orbital, radius of these polar satellites, and you can complete, you can find what is the area that the satellite can cover for one rotation, because by 7 rotations it can cover entire area of the Earth. You know, entire area of the Earth you can find by using 4 pi r squared equation. Radius of the Earth we know. Then actually very interesting part that very simple. Actually I think you can understand with general knowledge and physics basic equations. But directly this is not in the syllabus, but you can understand this, right? This is polar satellites. Then try to find radius of them, try to find time period, try to find velocity, try to find energy of that, try to find binding energy to remove that one, find the energy need to launch that from the Earth's surface, everything you can do as I did before. Right. Next one I am going to explain about Lagrange satellites. It's also very, very important satellites. We can use Lagrange satellites to observe in between Sun and the Earth and beyond the Earth. Right. What are the Lagrange points? It's simple principle. You can see this is Sun. Sun is here. Earth is here. Actually, we can find 5 Lagrange points around the Sun due to the effect of gravitational field. Three of them are located here, here, and here along an equilateral vertices of an equilateral triangle. Lagrange point means actually at that point, right, forces are balanced. At that point, forces are balanced. The points where forces are balanced are known as Lagrange points. Then actually we have 5 Lagrange points, one of them here, another one here, another one here, right? They are located at vertices of an equilateral triangle. Distance between the Earth and the Sun we know normally 1.5, 10 to the power 11 meters. And we can find another 2 Lagrange points here and here. L1 and L2. Another Lagrange point L3 here, L4 here, L5 here. 5 Lagrange points we have. That means these points are in equilibrium, right? No resultant force acting. Then here, this L3 and L4 points we can use after, I think, long time to create artificial colonies, right? L1 is used to launch a satellite. We can place a satellite L1. If satellite is placed at point L1, it doesn't move relative to the Earth and the Sun. That means these points are stationary relative to both Earth and the Sun. When Earth rotates, L1, L2 also rotating in the same manner. Then always L1 will be at the same point relative to the Earth and the Sun. And related to the Earth and the Sun, L2 will be at the same point. Then if you place satellites here and here, this satellite can observe in between Sun and Earth everything. This satellite can observe away from the Earth everything. Actually, we have equations there. It is hard to solve, but you should be able to write equations only at least, right? Here you can take radius capital R, radius of the orbital of the Earth, normally you know it's 1.5, 10 to the power 11 meters. Assume this distance here to here, x. And here to here, y. Mass of this satellite M1, mass of this satellite M2, mass of the Earth, simple M, mass of the Sun, capital M. Then I can write equation for this satellite first. When you are writing equation for satellite M1, which is located at the Lagrange point L1, you have to consider two forces, force given by the Sun, force given by the Earth. Then resultant force towards the Sun, I can write this force, attraction given by the Sun minus attraction given by the Earth. Then I can write again same equation, F equals G capital M, simple M, over R squared equals M R omega squared. This equation. Here resultant force I can write Gm over distance squared. Towards the Sun I can write G capital M, mass of the Sun, mass of the satellite M1, separation squared. Separation R minus x, here to here distance, R minus x squared. This is a force acting on this satellite, force given by the Sun. And force given by the Earth we have write G M over, they are in the opposite direction, they are not in the same way. Opposite, therefore resultant we have to take by the difference of them. G mass of the Earth, mass of the satellite, separation x. squared, mass of the satellite, radius of the orbital, capital R minus x, radius, capital R minus x, omega squared we know, 4 phi squared over time period squared. Time period 365 days because it rotated the earth simultaneously. Then this is the Lagrange equation for the M1 satellite. GMMOR squared, GMMOR squared, MV squared over MR omega squared. Omega 2 phi over T squared, 4 phi squared over R. Now for M2 you can write attraction this way given by the earth, attraction given by the sun equals again same thing. Then two forces I can write G capital M M2 over Gm M over distance R plus Y. R plus Y squared. Attraction given by the sun and attraction given by the earth plus same direction Gm M2 over Y squared equals mr omega squared. Now radius r plus y, m mass of the satellite, r plus y, mr omega squared, 4 phi squared over time squared. You can see time squared again 365 days. Then actually these are the basic things in our syllabus. Then study them well. And if you want to watch again previous videos, you can use channel NIE YouTube. Then you can see these lessons again. Then anyway, try to do these questions. They are very important, and try to do all the past paper questions. Then thank you very much for